Hi again, it's Anna, Annie, and Chris. This is number 3, part B. Very similar to part A, so I'll go through this a little bit quicker. The only main differences is that we are switching the the expressions, and instead of infimum, we're looking at the supremum. So again, in number 3, part B, for any sequence a sub n of positive numbers, we want to prove that the limit supremum as n approaches infinity of the nth root of a sub n is less than or equal to the limit supremum as n approaches infinity of a sub n plus 1 over a sub n. And here is the proof. Once again, we're going to let the limit supremum as n approaches infinity of a sub n plus 1 over a sub n be equal to alpha, which will be less than beta. We also know that there exists an element n in the set of natural numbers such that lowercase n is greater than uppercase n. We can then imply that a sub n plus 1 over a sub n is less than or equal to beta. Multiplying both sides by a sub n will produce and imply the following expression here. A sub n plus 1 is less than or equal to beta times a sub n. And once again, very quickly, I will manipulate this by switching this lowercase n to uppercase n. And then in the next few steps, just continue increasing each side, as we saw in part A. And then continuing that until we can make a general statement of a sub n plus k is less than or equal to beta to the kth power times a sub n. We are once again going to let lowercase n, which is greater than uppercase n, be equal to n plus k. And manipulating that, we get k is equal to n minus 1. Once again, I'm going to replace this n plus k with a lowercase n, and this k here as an exponent with n minus n, producing this expression. A sub n is less than or equal to beta to the n minus n power times a sub n. Just lower that a little bit once again. What I will do next is take the square nth root of both sides, which will imply this expression here. And just as before, I will manipulate this right-hand side by expressing the subtraction of exponents in terms of division, as seen here. And then the nth root of beta to the nth power is simply beta, which can be pulled out, leaving us with this expression here. So just to clean it up, once again, we'll take this initial left-hand side and set it equal to what we've developed on the right-hand side. We'll bring this back to the next screen for more room. We'll take this expression here and take the limit as supremum, as that should have said supremum. My apologies for this. Supremum of both sides as n approaches infinity, producing this expression here. And again, by the theorem that we proved in last semester, as well as stated by theorem 3.20 part B in the text, we know that this limit here is equal to 1. So I can replace this with 1. This approaches 1. And the limit of beta, which is a constant, is simply beta, giving us the expression that we see here. Oops, where did that go? Here we go. So therefore, the left-hand side remains. The limit as n approaches infinity of the nth root of a sub n has to be less than or equal to simply beta. Very similar explanation of before we state the next part. This is true as beta is greater than alpha. So once again, if I let this expression be x and show you that on the number line, we have alpha. And beta is this time is greater than alpha. But x is less than beta. So if I try placing x here, I could then bring beta even closer to alpha, which will cause this x end up on this side, because beta again is very arbitrarily close to alpha, implying this statement here that the limit as n approaches infinity of, again, little typo here, supremum, try to cut and paste, as the nth root of a sub n has to be less than or equal to alpha. That limit here is expressed by the x on the number line that I've demonstrated, which we can see is less than alpha. And if that is less than alpha, and once again in the beginning of the proof we did let alpha be equal to the limit as in supremum, once again supremum, I'm going to have to make those changes before I submit my assignment, as n approaches infinity of a sub n plus 1 over a sub n was equal to alpha. So I can replace this alpha here with that expression, and that is exactly what we wanted to prove in the beginning of part B, as you can see here. Therefore, this proof is now complete. Thanks, and I'll see you in class on Monday.